Am I recording? I'm recording. Sweet. All right. So we are in kind of our last part of Unit 3 here, which is another type of application and word problem scenario with derivatives. So I kind of compare it to related rates. It's the same type of problems, just, doing a little bit different math. The word problems, application, and derivatives again. And it's called optimization. That's the word here, optimization. We're finding the optimal something, all right? Usually we're trying to maximize or minimize, maybe maximizing area or minimizing cost, something along those lines, okay? It's kind of approached the same exact way as related rates, trying to draw pictures, trying to identify unknowns, all that stuff, okay? So let's go through the steps that kind of guide us along the way here. So number one, it's pretty obvious, but it's kind of like with related rates. You got to understand what the problem's asking you. Okay, you got to figure out what the unknowns are. What is the given quantities, and what are the given conditions? So we're going to break all this stuff down. Just like with related rates, if you can draw a diagram or a picture, do that. Identify the given and the required quantities on the diagram, just like with related rates. And then introduce notation. Okay, so whenever we're doing this, it's just like related rates. We're trying to create an equation here. And we're going to assign a symbol to the quantity that is to be maximized or minimized. That's what optimization means. It means we're maximizing or minimizing something. Trying to find the maximum value or the minimum value with given conditions. That's what maximizing and minimizing means. It's trying to find a max or minimum quantity given certain conditions. But whatever equation we're trying to maximize or minimize, we're going to call it Q just for notation purposes. And we're going to select symbols for other unknown quantities. Okay? So once we figure out Q, we're going to express Q in terms of some of the other chosen symbols or other variables. Again, we're just creating an equation like with related rates. All right, so if Q has been expressed as a function of more than one variable, we're going to use these equations to find relationships in the form of an equation among these variables. Then use these equations to eliminate all but one of the variables in the expression for Q. All right, this right here, this just means, number 5 just means we're going to find an equation with one variable. So if you want to summarize this as one equation with one variable, we'll see how that works here in a second. Number 6, I think, is really important. I think it's important to state the domain of your equation because sometimes variables and answers we find won't be within the domain. And then lastly, number 7 is to find the absolute max or min value of f, which we know how to do from our first day of this unit. Okay, all that being said, let's try a problem. You'll see all these steps kind of in application. I like this problem. I think this is a very good problem to start with. Okay, so 1, an open top box, so a box with an open top, is made by cutting congruent squares of side length x from the corners of a 20 by 25 sheet of 10 and bending up the slides. Think about that image for a second. We'll draw it, but think about what that looks like. That being the case, what we're doing is we're trying to figure out how large the cutout square should be so that the box can hold as much as possible and find the resulting maximum volume. So before we start anything with any of these problems, I always ask myself, what am I trying to optimize? Is it maximizing or minimizing? And I think we can tell that it's going to be maximizing. Maximizing what? What are we trying to maximize here? We're trying to maximize volume. Okay? That is what is being optimized here. We are trying to maximize volume. So that volume equation needs to be my Q. It needs to be what I'm trying to maximize here. Okay? So Let's think about how this works. Let's draw a diagram to kind of help us along the line here. We got a sheet of tin. All right, this tin is 25 inches by 25 inches. Okay. Now, what's happening is we're cutting little squares out. Okay, these dotted lines we're cutting out, and these sides are going to be length x. Do we see that? Do we see we're going to cut out squares of length x from this sheet of tin? And what it's saying is we're gonna have a shape that when we cut those little squares out, we're going to fold along these lines here. So if I fold along these lines here, it's going to make the shape of an open box. Okay, you cut out the dotted line and you fold up the sides and you have a box. Now there's multiple different shapes of the box that we can make depending on how big of a square that we cut out. So we got to ask ourselves, we got to figure out what the dimensions have to be to make it where we have the maximum volume. This sheet of tin being 20 by 25, that's my conditions. Okay, so given these conditions, we're trying to maximize volume. Okay, so whenever, this is pretty simple, whenever you figure out what you're trying to maximize, go ahead and just write the equation for it. Write the equation with all the variables, just the generic equation for volume. Well, the volume of a box, we know, is length times width times height. That is what we're maximizing, is a volume equation with length times width, not times height. Now, before we can call it a Q equation, I always keep track of this over here to the side. There's two criteria that needs to be met. Number one is it has to be one variable. And number two, it has to be simplified so we can take the derivative. Okay? It has to be one variable, usually in terms of x or something, so we can take the derivative and maximize. And then it has to be simplified so we can take that derivative. All right. We know the equation is volume. It is not one variable because we have L, W, and H. So it is not one variable. That's what we're going to try to do. So we create the equation that we're trying to maximize, and we get these two conditions right here, number 1 and 2, so we can actually solve this problem. And then once we do that, it's just solving a derivative problem. And you're going to see it's pretty simple. All right, first things first. What's our dimensions going to be? What is going to be our variable that we can get these all in terms of? All right, well, think about this. Usually I have a little bit more discussion. Since this is a video lesson, I'm just going to kind of talk about it. If I were to cut out a length of side X, okay, and I fold it up, wouldn't you agree that that's going to be my height if I fold that up? So my height in this case is X. Okay. Now, is there some way that I can rewrite length and W also in terms of X? Well, think about it. Think about this length right here. This length right here is going to be 25 subtract 2 values of X. Wouldn't you agree that the length is just the entire sheet subtract 2 values of X? And then I'll be left with the length of my box that I fold up. So length is nothing more than 25 minus 2x. And the width is going to be the same thing. The width of my box, if I were to cut out these little square corners, is going to be the entire 20 subtract 2 values of x. So this is 20 minus 2x. Okay? So currently, right now, this volume is one variable. Check. Okay? Everything is in terms of x, and it's the equation that we're trying to maximize. We're trying to maximize volume. Okay? Awesome. Okay, so we got our maximum volume here, or we got our volume equation that we're trying to maximize. Now, before we take the derivative, I want to simplify it a little bit. Okay, I don't want to take the derivative of this. I want to take the derivative of something a little bit more simplified. So that's the next step. So what I would do is, this is just distributing x and then doing a distributing. That's all you have to do. So take 1 second now. I'm going to pause the video, or I'll give you a second if you want to FOIL that out. And I'll just go ahead and write out what it's going to equal. After all is said and done, this is what volume equation ends up simplifying to. So now, number one is it's one variable, all in terms of x, and number two, it's simplified. Okay. So now I can call this my Q equation. We use Q to notate when we make the shift from the equation to what we're trying to maximize. I'm trying to maximize this equation. And it's real simple. All we have to do is take the derivative and find the maximum value. We know how to identify a maximum value. Okay. So what we're going to do is take this derivative. That's all we have to do is take the derivative. We get 500 minus 180x plus 12x squared. And if I'm trying to identify maxes and mins, or in this case maxes, you need to set it equal to 0 and identify the critical points. Okay. All right, well, if I'm fattening this, it looks like we actually have it being divisible by 4, it looks like. We can divide everything by 4. We get 125 minus 45x plus 3x squared equals 0. And I'll go ahead and save you a little bit of stress here. I don't think that there are any factors that would that makes this factor nicely. So in this case, I'm going to do the Pythagorean or quadratic equation. A negative b, which would be 45, plus or minus the square root of b squared, which 45 squared is 2,225, minus a times, or 4 times a times c, which c is 125, all over 2a, which would be 6. Okay, that's just the quadratic formula there that we've done in the past when we can't factor. And this ends up being 45 plus or minus the square root of 525 over 6. All right. Now, I would like to keep this as the exact values, but it looks like we have 2 separate values here, which if I were to just give an approximation, we get 11.318 and 3.681 for x. X is approximately equal to those 2 numbers. Now, this is one thing that I wanted to touch on, and I should have done this at the beginning of the problem, and I will start to do it at the beginning of the problem. But what's my domain for x? What can x be? X is the value of my height. It's what I'm cutting out the squares on my piece of tin here. Can it be negative infinity to positive infinity? Well, no, it can't be any negative length. Lengths can never be negative, so I know it's going to be 0. Now, can you say infinity? Can I cut an infinitely large piece out of this? No. What's my restraint? I know it can't go past 20 or 25. I know that much. But think about it. Can I ever go past half of, say, 20? Because if I go past half 20, say I want to cut a length of 11. Well, I cut out a piece of 11 right here, and there's only 9 left over, so I can't cut out a piece of 11. Can I cut out a piece of 10? Well, if I cut at 10, I'm cutting it directly in half, so I'm not giving it any length. It has to be all the way up to a length of 10. There is no way to cut any length past 10 or right up to 10, because then I wouldn't have enough to cut on both sides of this 20. I would be cutting it in half or more, and I would not have enough depth to create a box. So keeping that in mind, keeping my domain in mind, x equals 11.318, we can reject that. And I want you to, if you ever get an x value that's not in your domain, I want you to write that we reject it. Okay? So the only critical point within my domain is 3.681. Okay? So the only other thing that we need to check is our endpoints. Okay? So if you notice, 0 is not within my domain. Okay. The only other endpoint is 0, and if I plug 0 into this, then we just have a flat sheet of 10. So our endpoints do not work here. We have a volume of 0, or the other endpoint does not work. We get that X has to be this length right here, 3.681, in order for this to have a optimal volume. But we have to make sure, this is always the last step, we have to make sure that this is indeed a maximum value. So what we're going to do is we're going to test. It's approximately 3.681. Okay, and we're going to test it on a number line because it's a critical point. We want to see if it's positive on the left and negative on the right, meaning that it will be a maximum. Okay, so you always have to test it. In optimization problems, they want to see you testing. So if my derivative function is this function here, it doesn't factor nicely, so we're going to have to test points in that big thing. Maybe test 1. If I test 1, that's 500 minus 180 minus 12. That is a positive number. And if you plug in some number like 10 or 20 or something, then, I mean, test maybe like, I don't know, 10 or something. I'll go ahead and tell you that is definitely going to be a really big number plus a negative number, or plus a big negative number. It's going to end up being negative. You can test points as much as you want. You can test 4, 5, 6, or 7, or 8, whatever. You're going to end up getting a negative number there. Okay. So it says find how large our cutout squares should be so that the box is having a maximum value. So in this case, those lengths need to be approximately 3.681, we'll say, inches. To give the exact value, it'll be 45. It'll be minus the square root of 525 over 6, which is approximately 3.681. So having that cutout of a square is going to result in our maximum volume. We figured that out. We maximized it. We found an equation for volume, and we found the maximum value, all right, that would give us a maximum volume there. If I want to know what that maximum volume is, I just plug it back into my original equation, all right? And I can do like the approximated value just to show it. I don't really want to write out the entire thing to confuse everybody, but if I did 25 minus 2 times 3.681 times 20 minus 2 times 3.681 and then times 3.681, all right, that was what my volume equation was in terms of X. I would get my resulting value would be my maximum volume, which in this case, I'll do it really quick and you can try it on your own, but in this case, an approximated value of 820.528 inches cubed. So that's my resulting maximum. And we just plug that back into the original volume equation, or I guess the original Q equation. And we got the resulting max given the conditions. So let me give you just a quick guide here, exactly what we did, that works every single time. So what we're supposed to do is, number 1, create that equation. Okay. Number 2 is to get that equation one variable and simplify it. Number 3 is to take the derivative. All right, take the derivative. Number 4 is to solve for x. And then number 5 is to test. All right, to test that x value to make sure it's indeed an absolute max. Okay. And whenever you determine that it is a maximum, you want to answer the question. Okay. In this case, the volume that results in the maximum volume is 820.528 inches cubed. All right, let's try these steps again in another problem. I'll do one more, and I'll save the last one for for class. So I got this one and this one. This is a good one we can do in class. Ooh. All right, I'll try to do at least one more. We'll do probably this one. All right, so let's try to break it down again. So it says find two positive numbers whose product is 100 and whose sum is a minimum. Okay, so start with finding that minimum or maximum word and identify what we are trying to minimize or maximize. In this case, we are trying to minimize the sum. We're trying to figure out the smallest sum given the condition that the product is equal to 100. All right, so I'm going to write that down. Minimize sum. So we need to create an equation for sum. Okay, sum equals, what's the sum? Well, two positive numbers. A sum of two positive numbers is just x plus y. There we go. So, number one, we just did. All right, we're trying to figure out what equation we're trying to minimize. In this case, it's the sum. Now, number two, all right, is to figure out how to make a Q equation from that. All right, so we can find the derivative and actually find what the minimum value is. Number one is we got to get it one variable, which in this case it's not because we got both x and y. So we need to get this in terms of just one of the variables. So how do we figure that out? Well, the conditions are always what allows us to do that. In this case, the conditions are that the product has to be 100. And can I not use that condition to isolate one variable and substitute in? Sure, why not? Say that y equals 100 divided by x, and we can plug it in. So my sum equals x plus 100 over x. And we can check this criteria off. It is one variable. Number two is we're trying to figure out, is it simplified? Meaning, is it in a form I can take the derivative? I could probably simplify this a little bit. What if I say x plus 100x to the negative first? That's my Q equation. It is one variable. It is, and it's simplified. So then number three is we take the derivative. Okay, number three is we take the derivative. So we get 1 minus 100x to the negative second. That's the derivative using the power rule. And we set it equal to 0 and solve. Okay, that'll be step 4. So these are kind of my steps as I go through this. Number one, we created that equation that we're trying to maximize. Number two, we got it into its Q form. Number three, we take the derivative. And then number 4 is from 4 down, or actually from 3 down, is really no new math. It's all common math. Okay? All right. So I set this equal to 0 and solve for x. Let's keep going with this. We got 1 minus 100 over x squared equals 0. We can get a common denominator. We can just solve. Okay, maybe we can subtract 1. We get negative 100 over x squared equals negative 1. I can multiply both sides by negative x squared, and I can get 100 equals x squared. And then x equals, if I take the square root, plus or minus 10. Now, I got 2 answers for x, but are both of those a part of my domain? 2 positive numbers. So you always got to consider the domain once you solve for x. See if both of those fall within the domain. If any of them don't, we reject it. So we're going to reject negative 10, not in domain. So we only get x equals 10. Now, that's step 4, is figuring out the x value. Step 5 is testing it. So we're going to test x equals 10 and identify if it truly is a minimum value for this sum. Okay? So we're going to have our Q prime equation. That's what we're testing right here. We're going to test the value 10. The domain is any positive number, so 0 on to infinity. Okay? But we're going to test to see if this really is a minimum value. So if I look at the derivative value, which is right here, is the one probably I want to test it in. If I plug in, say, like 5, okay, 1 minus 100 divided by 25. So that's like 1 minus 25, or 1 minus 4, I guess. That's a negative number. Anything greater than 10 is going to give you a fraction less than 1, so 1 minus that fraction is going to be a positive number. So this is good enough justification. You can say that this is a minimum value. We can check that justification off. And then step 6, my final step, is to just answer the question. Okay? So we know that x equals 10 is going to be that last, or that value that gives me the minimum sum. And it just says find two positive numbers. So we got that x equals 10. Now all we got to do is figure out what y equals. Well, since we know that the condition is that that equals 100, we can easily solve for y, right? So there you go. X equals 10, y equals 10 are our most minimum values here. Okay? Meaning, if I add these sums together, so it didn't ask for this, but the minimum sum equals 20. There is no way to get a product of two positive numbers to be equal to 100 whose sum is less than 20. Okay? So same steps every single time, right? The only new thing really to this is numbers 1 and 2, being able to create this equation and being able to get it one variable and simplify it. And then once you get that Q equation, once you get that equation we're trying to maximize or minimize, it's just derivatives set equal to 0 and solving for a maximum or a minimum. In this case, we had a minimum value. We have no other values to check. It's not a closed interval, so we are set. We are good to go. All right, tomorrow in class, I'm going to try this problem. This is probably the hardest problem I got on the notes, but it's preparing you for harder problems. So I think it's a good one that we try together. You can try it on your own. And then this is also a question I have on my test. So I think this is also a good one that we should do together. So I got 2 questions we're going to do in class. Plenty of practice in the book. And then discussing what will be on the quiz the following day. All right? So less than 30 minutes, we made it today. Good job, guys. Hope that y'all have the best day ever.